The sound in the video. Is this board oriented correctly? Because I think somehow the angle is different. I don't know if this is okay for the video. Yeah? Okay, good. Thanks. So today I'm going to talk about two algorithms. In the first hour, I'm going to talk about Shor's quantum algorithm for factoring large integers. And in the second hour, about Grover's algorithm for search. So let's start with Shor's factoring algorithm. So what is the goal of the factoring problem? It's that somebody gives us a large integer, like 15, and asks us to like find the prime factors of this number. So given an integer n, capital N, find prime factors of n. And in fact, it's good enough if you have an algorithm that finds one prime factor, because then you can just divide that out and continue with the resulting smaller number and find a factor of the smaller number, etc. And you should think of this as large. And as you probably know, like this problem is supposed to be classically hard in the sense that it takes much more than polynomial time in the input length being the number of bits with which you need to write down capital N. And a typical input size is if the number capital N has like 1024 bits or maybe 2048 bits. These are the typical integers that you would encounter in cryptography. So if you can factor integers of this size, right? So I'm not talking about n equaling 1024. I'm talking about n being written down with 1024 bits, which means that the magnitude of capital N is something like 2 to the power 1000 or 2 to the power 2000. These are very large integers. And we don't know how to do this classically in any reasonable amount of time. That's why cryptography based on this problem, at least until the advent of quantum computing, is considered secure. So this is probably, because we can't prove any of these things, but this is probably hard for classical computers. As always, by the way, feel free to interrupt me with questions, complain if stuff is not readable or otherwise incomprehensible. And the best classical algorithm is the so-called number field sieve, best known algorithm. Takes time something like 2 to the power log capital N to the 1/3. So log capital N, that's the number of input bits, right? If you have a number of 1000 bits, then this number here would be 1000. This is better than just like brute force exponential time, which would be 2 to the power log capital N, but it's much worse than polynomial time in the input. So this is a very slow algorithm. Like if you're trying to run this best known classical algorithm to factor a 1000-bit number, like forget about it. This is going to take a very long time. And this hardness underlies the safety or the assumed safety of RSA cryptography. And that means that coming up with an efficient algorithm for the factoring problem is a very big deal, right? This RSA cryptography and things that are very similar to it are used to protect all online commerce, credit card payments, etc. Like trillions of dollars are being protected by this cryptography. If somebody comes up with a fast algorithm for factoring large integers, all this stuff breaks down. And this is one of the main impacts that a quantum computer will have. And we really need to find alternatives for RSA cryptography and also elliptic curve cryptography. And people are working on that. But really, that's not the topic of today's lecture. What I would just want to explain is this factoring algorithm, right? So this is to impress upon you that this is a very important problem in practice and not just some mathematician's toy thing. So Shor's algorithm factors numbers It factors n using roughly log n squared gates. So it gives a circuit with this many gates. I mean, there's like log factors hidden here, etc. But this is a very reasonable polynomial in the length of the input. So think of this as a very efficient quantum algorithm. And of course, we haven't really run this thing yet on large integers. Like I think the largest number that has been factored with Shor's algorithm on an actual quantum computer was either 15 or 21. I don't remember which one. Neither of them particularly hard. But if people succeed in building a very large quantum computer, something like, say, with maybe 1 million reasonably behaved qubits, they don't have to be perfect, but reasonably behaved, you could start breaking RSA based on keys of roughly 2,000 bits. This is somewhat far away, but it's not completely out of the question. Like the most ambitious companies, they have roadmaps where they would get to 1 million qubits, maybe around 2030 or so, maybe 2035. So this is not like very far future, at least in the optimistic plans of these companies. Right? Maybe this will all fail, who knows? But if cryptography has a risk, then we have to take it seriously, because if the predictions of these companies or their ambitions pan out, then a lot of our, let's say, online protection is going to break. So Shor's algorithm, that's what I want to explain now. It consists of two pieces. The first piece is a classical reduction from the factoring problem to some other number theoretic problem, which is called period finding, which I'll explain first. So classical reduction from factoring the number capital N to finding the period of some function f, which I'll explain. And this is classical. And then the second part of the algorithm, this is the actual quantum part. This is an efficient quantum algorithm for this period finding problem. So these are the two things I will explain in this hour, starting with the first, the classical reduction. So how to go from factoring to periodicity finding. And the way you should read this arrow is what this means is if you could do efficient period finding, that suffices for factoring. So we need to define a function f, which I'll define. And I need to show that that this function is periodic and that its period tells you something about the factors of the number capital N. Okay, so here goes. So first we pick a random integer. I'll call it x in the integers between 2 and capital N minus 1. And this is something you can easily do. You can pick a random integer just by flipping the bits of its binary representation. For instance, this is cheap. And then you want to check if the greatest common divisor between x and n is greater than 1 or not. So the greatest common divisor between two integers, it is just what the name says. It's the largest integer that divides both x and n. And this number is actually efficiently computable classically by something called Euclid's algorithm. Right, so suppose you compute this GCD of x and n, and out comes some number, let's say 29 or something, rather than 1. At that point, you're actually in good shape because that number is going to be a non-trivial factor of capital N, which means you found one factor, right? And if you find one factor, you're in good shape because then you can just recurse. So this is actually the happy and unlikely case of the algorithm. So this is happy but unlikely. It's much more likely that the GCD of x and n is equal to 1, that there is no non-trivial common divisor of x and n. But if the GCD of x and n is equal to 1, you can do something else. You can define an interesting function that's going to be periodic with an unknown period r that's useful for factoring. So you define a function that goes from the integers to the integers mod n. But this notation here just means the integers modulo capital N. Does everybody know what this means? And the function is defined like this. On an input integer a, I'm defining fa to be x to the power a modulo n. This is called the modular exponentiation function for obvious reasons, right? You stick in a number a, and it puts a in the exponents, and everything goes modulo capital N. Notice that the x is fixed here. It's the same x that we chose in the first line. And this f, this is actually efficiently computable classically by something called repeated squaring. I'm not going to explain it, but it's important to keep in mind that this f is not some super complicated function, but it's efficiently computable. If you're curious about how this is done, you can ask me in the break. It's a little exercise to show that this f is efficiently computable. And when I say efficiently computable, I always mean like polynomial time in the number of bits that are needed to write down capital N. Now, if you know a little bit of group theory, then you can look at sort of the sequence of numbers that is generated if you stick in sequences of a's into this function, right? A is 0, a is 1, a is 2, a is 3, etc. And you'll see that the sequence of numbers generated is actually a so-called cyclic group. It's a cyclic subgroup of the set of all integers that are co-prime with n. If you don't understand what that means, that doesn't really matter. But the sequence x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, etc. This is going to cycle. It's going to return. So the first number in the sequence is 1, even modulo n. And this is going to return to 1 at some point. This is a cyclic sequence. Or in other words, the function f is a periodic function. Right? If you stick in the numbers 0 up to r minus 1, you're getting all distinct values. And then that sequence of r numbers is just going to repeat if you stick in bigger integers. So f is a periodic function. With some unknown period r. And I'm underlining the word period r here because finding this number r, this is what the second part of the algorithm is all about. And you can show that with high probability, and I'm not going to prove this. This is some combination of elementary number theory and a bit of probability. So with high probability over the choice of x, this unknown period r will be an even number, so a multiple of 2. And the number n does not divide the numbers x to the r over 2 plus 1 and x to the r over 2 minus 1. You'll see in a second why these assumptions matter. Just believe me that this is going to happen with high probability. So let's just assume that this period r, this unknown number that we would like to find, is an even number, and that n does not divide x to the r over 2 plus 1, nor x to the r over 2 minus 1. All this stuff, by the way, is, I think, 18th century mathematics, so these things were long known. Okay, so this defines some function that's sufficiently computable and that has an unknown periodicity r in it. And now let me show you why finding this number r helps you to factor the number capital N. So how does finding r help to factor N? Is the video still okay? Because it's quite dark in this corner. It's good? Okay, thanks. Right, I told you that you can reduce the factoring problem to the period finding problem. So now I need to show you why it suffices to find this number r. How this will tell you some of the factors of capital N. Okay, so here goes. What do we know about this period r? We know that x to the power r equals 1 modulo n. Right, in fact, r is defined as the first time that this sequence returns to the number 1. So by definition, x to the power r equals 1 modulo n. Now, let me do something super complicated. This is the same as saying that x to the r equals x to the r minus 1 equals 0 modulo n. Right? Even if you haven't had your morning coffee yet, this step should be easy to follow. X to the r is actually the square of x to the r over 2, because we're working under the assumption that r is an even number. So we can also write this as x to the r over 2. Maybe I should write this here. The square of x to the r over 2 minus 1 is 0 modulo n. And this is sort of a nice form. This is something of the form, let's say, z squared minus 1, which you can write. This is called, I guess, strange product in English. You can write this as x to the r over 2 plus 1 times x to the r over 2 minus 1. And this is still 0 modulo n. Right? All of these are simple algebraic manipulations. And what does it mean for this number here to be 0 modulo n? It means it must be some integer multiple of capital N. So there exists some k, some integer k. Maybe it's in z, it doesn't really matter. Such that x to the r over 2 plus 1 times x to the r over 2 minus 1 equals k times capital N. And then we don't know what this k is, and we don't know what this r is. There's lots of stuff in this equation that we don't know. But the point is that if you think about the factors of capital N, right? Think of the simple case, for instance, where N is the product of two primes, P and Q. Those factors must occur here because every number has a unique factorization into prime numbers, including the number k times n. And that means that the factors of capital N, they also must occur either in here or in here. So all the factors of capital N, they occur on the left-hand side. All the prime factors of N occur in the number x to the r over 2 plus 1 or in x to the r over 2 minus 1. And now we're almost there, because what we can do is we can now compute the greatest common divisor of capital N with this number as well as with this number. We compute both of those GCDs. And I claim that those numbers will actually be non-trivial factors of N. So both GCD of x to the r over 2 plus 1 with N and GCD of x to the r over 2 minus 1 with N are non-trivial factors of N. So there you go. If you find this period R, and this event that R is even and it does not divide these two numbers occurs, which happens with high probability, then you can just compute two GCDs and it will give you factors, non-trivial factors of the number N, which means that if you find R, you can factor. And you might be a little bit worried here that what could happen actually, what could go wrong, is that this number here shares some non-trivial factors with N because it is actually itself a multiple of N. And it could also be that this number here is a non-trivial factor of N because x to the r over 2 minus 1 happens to be a multiple of N. But we've actually excluded that here. So the assumption that N does not divide this number and the assumption that N does not divide this number means that these two GCDs, they won't be N itself, but they will be a non-trivial factor of N. Okay, this is a little bit technical. It actually has very little to do with quantum. So if you're worried by the number theory or confused, just forget about it for now. The main thing, the take-home message of this part of the talk, is that finding R helps you to factor the number N. Right, so what it boils down to now is we need some algorithm, and it's going to be a quantum algorithm, which, given the description of this function f, actually finds its period R. Okay, so now I want to move to the second part, the actual quantum part of the algorithm. A quantum algorithm for period finding. But before I go to the quantum part, let me pause for questions. So are there any questions about this number theoretic reduction? Yes, please.
Actually, R is not even, or
yeah, so this assumption, this could be wrong, of course, right? And then what happens is you can find this period R, you can compute these GCDs, and you will actually discover that those may not be factors of capital N. But that is something you can easily detect. Because you can do division. Division is something you can do very efficiently on a classical computer. So you just run your algorithm, right? You sort of hope and pray that this condition holds, even though you don't know whether it holds. Some numbers come out. You check if they are actually non-trivial factors of N, and if not, then you repeat with a fresh choice of X. And again, in your second repetition, you're going to have a high probability that this condition does hold. So you keep repeating this until the two numbers that come out of the GCD computations are actually non-trivial factors of N.
yeah. The check input finding out, like first.
No, the check is just, so this thing here is going to spit out a number, an integer. This thing is going to spit out a number. You have to know R. Well, I mean, like you can do this whole calculation with whatever R tilde your quantum algorithm produced, right? And it might be the wrong R tilde. You can stick that R tilde in this calculation. Maybe the calculation gets stuck somewhere because the R doesn't happen to be even. Maybe it gets stuck because some of these assumptions are false. The point is, at the end of the day, numbers come out and you can very quickly check if they are actually factors of n. Okay. If not, you repeat. Yeah, you had a question.
So if n in fact is prime, aren't you kind of stuck endlessly long in trying?
Yeah, that's a good point. So I think there are two sort of extreme cases where this algorithm is not going to work. One is, n is itself a prime number. Now, this is something you can already check efficiently on a classical computer. There are efficient classical algorithms for checking if something is prime, but not efficient classical algorithms for actually finding the prime factors. So you can kind of eliminate the case where n itself is prime from the start. And I think there's also a small issue if capital N is itself a prime power, you know, 3 to the power 200 or something like that. This is also something you can easily eliminate at the start. The really interesting case is where capital N is the product of two primes, which are roughly equally large. This is what people use in cryptography. And that's also the kind of thing to keep in mind, right? If capital N is the product of two prime numbers P and Q, then what will typically happen in this algorithm is that P is a factor of this guy and Q is a factor of this guy, or vice versa. And computing the GCD is then going to give you a multiple of P or a multiple of Q. And probably even P and Q themselves. And then you check if those are actually factors of n by just doing a division. Yes?
What is really this assumption of probability data?
So the random variable here is x. You pick your x at random. This x induces a function. This function is going to be periodic with periodicity r. This r may or may not satisfy these assumptions. The claim is that if you pick x uniformly at random, then with probability at least a half, these conditions will be satisfied. Right? You might think a half is not very much, but you know, if you have some algorithm that produces factors, non-trivial factors of n with probability 1/2, and you can check that the outputs are actually non-trivial factors, the expected number of repetitions that you need before succeeding is only 2. So that's quite small. So maybe I'll say with probability at least a half here to be more concrete. Other questions at this point? Yes, please.
N is very large.
Very large. I mean, for x, yeah, absolutely. So if x is a number of 1024 bits, sorry, if capital N, the number you want to factor, is a number of 1024 bits, then x will typically be also of that same size. But it's very easy to pick a random number of 1024 bits. You just flip 1024 bits and write this down, and this is the binary expression of your number x. There's an enormous amount of choice, but we're never going to do a search over the space of possible x's. We just pick one at random. We check if this GCD is greater than 1. If yes, then we are already done. And if no, then this whole story with the periodic functions kicks in. Let's see, what am I doing with time? Okay, 20 minutes, that's good. Okay, so if there's no further questions, then let's move on to the quantum part, which is really the more interesting part for the purposes of this school. So I'm first going to write down, sorry?
The ST is from, there is a
yeah, this is an abbreviation of such that, right? There exists an integer k such that this holds. Okay, good. Thanks. Other questions online? Yeah. You want me to close it? Okay, let me do that to see if that works. Should I or should I not? Okay, let me just try and see what happens. Okay. Yeah. Okay, is this better for the room? Better for the room, okay. Is it also okay for the video? Okay, good, then I will work with that. Okay, so what I'm going to do is I'm first going to write down the circuit that actually does this. I'm going to write down the quantum algorithm, and then we'll analyze it. And it's kind of crucial, the crucial ingredient of the algorithm is going to be the quantum Fourier transform that we saw yesterday. And if you're used to, let's say, things like Fourier transforms in signal processing, then you're probably not too surprised, because Fourier transforms are used to sort of find periodicity properties of objects, right? Like you say, you have some musical signal or so, you can extract periodicity information using a Fourier transform. And at a very high level, that's also how the Fourier transform is used here. There is a periodic function, that's this f. We want to find its period. It should be kind of high level plausible that a Fourier transform could be useful here. And indeed it will be. Okay, so here's the circuit. So first I'm going to choose an integer q, which is a power of 2 in the interval between capital N squared and 2 capital N squared. This is an interval where the upper and lower bound of the interval differ by a factor of 2. So there's going to be a unique power of 2 in this interval, and you can efficiently find it. And in fact, this is going to be the dimension of the Fourier transform that we're going to use. So here's the circuit. It's going to have 2 registers. The first register starts out in zeros. And the number of qubits here is going to be log of q, binary log of q. Whenever I say log, I mean binary log, because I'm a computer scientist. Right, so q is a power of 2, so this is an integer, and we start with this many qubits in the first register. And we're going to apply a quantum Fourier transform of dimension q here. And we've seen yesterday that there is an efficient quantum circuit to implement this, so that's fine. And then there's going to be a second register, which also has a bunch of qubits. And here we're going to, in superposition, compute the function f. I'll explain what this is. So OF is a unitary that does the following. It takes base state a comma 0 and computes a fa, where f is this function here. And remember, this is efficiently computable, and this implies, with a little bit of massaging, that this OF actually, that there is an efficient circuit to do this. And this is thanks to the fact that you can just do modular exponentiation with the so-called repeated squaring trick that you can ask me about in the break if you want to know. And then what we're going to do is we're going to measure the qubits in the second register. I haven't told you yet how many qubits there are in the second register, but you can sort of see it from the description of OF. Right? The second register needs to have sufficiently many qubits to be able to contain integers modulo capital N. And that means that the number of qubits here would be like log, binary log of capital N. Let's say rounded up to the nearest integer. That's sufficiently many qubits to contain the range of this function. Right, so we're going to measure those qubits now. That's going to cause some partial collapse in the first register. You'll see what happens there in a second. And then we're going to do another QFT, another quantum Fourier transform, and then we're going to measure the first register. And then the claim is that what comes out here of the measurements, this will give us information about R. So the measurement outcome, it's not going to be R itself, but it will give us information about R. And remember, R, this periodicity, this is what we're trying to find. So the measurement gives information about R. And this is the number we're trying to find here. And I'll show you in what way you get information about R. Okay, so this is the algorithm, and the rest of this hour we're just sort of going to go through this algorithm and see what it does. Let me first actually sort of convince you that this is an efficient algorithm, right? There's two Fourier transforms, but those can be implemented quite efficiently in a sort of a number of gates that's quadratic in the number of qubits. And this OF here, if you work your way through the details of this repeated squaring, its number of gates is also like roughly quadratic, maybe slightly more than quadratic in the number of bits of n. So it's slightly bigger than log capital N squared many gates. And the funny thing is that this OF, this is actually the most expensive component of the whole algorithm, even though it's really like a classical reversible circuit to compute the function f on a given point A. Right, so all the components here consist of small circuits, therefore the algorithm as a whole is a small circuit. It doesn't use many gates. It's efficient. Okay, now let me make some space here to sort of work our way through the algorithm. Can I erase everything except for the rightmost boards? Is anybody still writing? Yes. Yeah. The A-cats. So remember, f is a function from natural numbers to integers mod n. So A here, this is always going to be a sequence of bits, and I interpret that sequence of bits as an integer A. And that integer A is the input to the function f, and that gives me a number here, modulo capital N. So this is really just a way of sort of a quantum, it's not even a quantum way, it's really like a classical reversible way to compute the function f. And I'm going to run this unitary, as you'll see in a second, on a big superposition over many different a's, computing the function f in superposition over many different inputs at the same time. Yes, yes, yes. Yeah, okay, this is something I said yesterday, like I'm always going to assume without saying that integers and sequences of bits are the same thing. You can always take an integer and write it down as a sequence of bits, and conversely every sequence of bits represents an integer. So I'm going back and forth between this without even saying so. Okay, let me make some space here.
Only works for this, exists only for these particular kinds of f's, not for general f's.
I mean, for every function f, there exists such a circuit OF. A is classical data. We know that classical data can be copied. There's no problem there.
Okay.
Yeah.
Thanks.
Yeah. Yeah. Just keep in mind this. In fact, let me leave this on the board for as long as I can and start by erasing this stuff, just to remind you what the f is that I'm talking about again and again. Okay, so let's trace the state as it goes through this circuit and see what actually happens. Let's track the state. Okay, so what are we doing here? In the first register, we start with a bunch of zeros and we apply a Fourier transform. And what this does is it puts this first register into a uniform superposition over all the integers A that are representable by this many bits. So we first go with a register, let's say, of q zeros and a second register of, let's say, little n zeros. I'm thinking of little n as the length of the number of bits of the number I'm trying to factor. So I'm doing a QFT on the first register, an identity on the second, and you get a uniform superposition over all the a's running from 0 up to q minus 1 of cat a 0 to the n. Right, and again, think of a as ranging over integers, even though these integers are written down as bit strings. And in fact, at this point, you could sort of complain that I'm doing something very stupid, and I am doing something very stupid, because I could have achieved exactly the same thing by just Hadamard gates. This would also have put my first register into a uniform superposition. So why do I do a QFT? Just for aesthetic reasons, it's kind of nice to have like two QFTs. There's a nice mirror structure to this circuit now, but it doesn't really matter. So we could also have done just Hadamard's here to affect the same thing. Yes? This is going to be the QFT itself. No. That's different from the phase estimation yesterday, where we used the inverse of the QFT. There is a way actually to present this algorithm as an application of phase estimation, but that's not how I will present it. Okay, so we generated a superposition over many possible inputs A to my function f. And just going through the circuit further, now what we do is we compute f in superposition on all of those A's. Right? And the costs of this big operation in superposition is just the cost of computing f once, because that's the beauty of superposition. Sorry, this is not right. So in my big superposition, I have now computed f on very many different inputs, 0, 1, 2, 3, 4, 5, etc., up to q minus 1. And all of these function values, they live in the second register in some way. Okay, so now we are here in the circuit. In fact, I should put these measurements a little bit earlier. Let's put them here. Right, so at this point in time, we're going to measure the second register. And what this is going to give us is a particular function value. So we measure a second register, the second block of qubits. And we see some value, some integer. Which I'll call f at s. It's going to be some value in the range of f, and I don't really know what s is. So s is an unknown number between 0 and r minus 1. Right, so the second register is now going to collapse to a classical value, namely a particular value in the range of f, this value fs. So we know at this point what fs is, but we don't know what s is. And we don't even care what fs is. The point is that this measurement on the second register is going to now cause a partial collapse on the first register. And maybe somebody can tell me what we're going to have left in the first register after this measurement outcome. Right, remember from yesterday what happens if you measure some of the qubits of a state, but not all of them. You're going to get a classical outcome for like a bit string for the qubits that you've measured. And the rest of the state is going to collapse to the basis states that are consistent with the measurement outcome that you got for your second register. So which A's are going to be left in the superposition if I measure the second register and I get a particular value fs?
Yes.
Well, you're going to get s, but you're also going to get all the other A's that have the same function value, right? And here the periodicity comes in. So s has a certain function value fs, but s plus the period has that same function value. S plus 2 times the period has that same function value. S plus 3 times the period has that same function value. So your first register is now going to collapse to a superposition of s, s plus r, s plus 2r, s plus 3r, etc. So first register collapses to a superposition ket s plus ket s plus r plus ket s plus 2r, etc. So this is actually a very nicely spaced superposition. Right? The basis states that are supported by this superposition are all separated by a number r. And remember, it's this r that we're trying to find. Maybe at this point I will erase this board and draw a helpful picture here. So let me draw a picture of sort of the basis states that we have left in our superposition of the first register at this point. The second register has served its purpose. We're not going to look at it anymore. So what we now have in the first register is something that looks like this. So here I'm going to plot the different A's, the different values of A's, and here I'm going to plot the amplitude. So we're going to have an A at the value S, and we're going to have an A at the value R plus S. And we're going to have an A at the value R plus S plus 2R. And so on. Right, so you're going to have these basis states that are spaced apart by the unknown period R. And this is going to go all the way to Q minus 1 because that's the biggest A that we stick into our function in the superposition. Right, and this initial offset is by the unknown number S. Right, so these peaks, they indicate which of the basis states have amplitude in our first register at this point. And all those amplitudes are actually the same, like we collapse to a uniform superposition of these basis states. And now what we're going to do is we're going to do a quantum Fourier transform. That's this Fourier transform. And let me draw a picture of what the distribution on the basis states or the amplitudes on the basis states are going to be after this Fourier transform. And in fact, the basis states that have support now are going to be essentially 0 and Q over R. Remember, Q is the dimension that we chose for the Fourier transform. 2Q over R, 3Q over R, 4Q over R, etc. So instead of being sort of spaced apart by R, if you do a Fourier transform, what you're going to get is you will have essentially the multiples of Q over R, the integer multiples of Q over R in your superposition. And it's not going to be exactly this nice picture because Q over R need not be an integer. In the interest of time, maybe I should skip the calculation. You can find it in my lecture notes. This is also ignoring phase information. So what the Fourier transform does is it sort of converts this superposition over particular basis states into another superposition over particular basis states. And the basis states in the new superposition are the integer multiples of Q over R. Essentially uniformly with like all having the same magnitude of amplitude. So now we measure this, right? We're now at the end of the circuit. We're going to measure the first register. And what do we get? The outcome of the measurement is going to be a random multiple of Q over R. Right, because this superposition, its support is on all the multiples of Q over R. If you measure it, you're going to see one of those multiples. You don't have control over which one you see. But now we're almost done because I have only a few minutes left. So finding R from the measurement outcome. So let's say that the measurement outcome, so it's some random multiple of Q over R. Let me say C times Q over R. And for simplicity for the calculation, let's just assume for simplicity that Q over R is an integer. Everything is still going to work with a little bit of extra technicalities if this assumption is not the case. So this is a number that we know. Let's call it B. This is our measurement outcome. So there's 4 variables here, B, C, Q, and R. And we know 2 of those. We know B because it's our measurement outcome. And we know Q because it is the dimension of the Fourier transform that we chose ourselves. And we don't know what are C and R. So you can rewrite this a little bit as B over Q equals C over R. And we know both of the numbers on the left-hand side. This is known to us. But that means we also know the ratio on the right-hand side. So this ratio is also known. And C is going to be some random integer. We don't know what it is, and we would like to find R. So if you know a ratio, C over R, and you would like to find R, it could be that you're very lucky and that C and R are co-prime to each other. And this happens with reasonable probability. So with non-negligible probability. C and R, the GCD of C and R is 1. So there's no non-trivial factor between C and R. And in that case, you can actually find R. Find R by writing the ratio B over Q in lowest terms, meaning dividing out the common factors of B and Q, which we know how to compute by Euclid's algorithm. And look at the denominator. So you take B over Q, you divide out the common factors. If C happened to be co-prime with R, if the GCD was indeed 1, then this denominator is R. Right, and this is not always going to work. It depends on whether or not this random multiplier C was co-prime to R or not. This doesn't always happen. It happens with non-negligible probability. And the same happens, I'm going to give the same answer as I gave before. Okay, this might not always work, but some number comes out, which is supposed to be a factor of n. You just check it, if it is indeed a factor of n, and if not, you repeat. And because the success probability of all of these sort of steps that should simultaneously succeed, the success probability is not too low, a small number of repetitions suffice. Right, and there's a lot of calculations that I swept under the rug, especially here, but for that I refer you to the lecture notes. Because I guess I'm out of time for this hour. More than that. Okay. So I hope the sort of the high-level picture at least is kind of clear. You take the factoring problem, you reduce it to the problem of finding some periodicity, and you use the efficient quantum Fourier transform to extract this periodicity information, which you can then translate back to information about the factors of n. So this is basically Shor's algorithm. And a lot of things were built upon this later. There's a whole spiel of something called the hidden subgroup problem, which is a much more general problem that you can solve with a very similar algorithm. It also breaks discrete logarithm cryptography and many other things. Any questions before we break? Okay, then I guess we break until 10:30, is that right? Okay. And there should be food and coffee downstairs. Yeah, thanks. Can I start? Good. Test, test, test. On, yeah. The video sound also good? Okay, good. Let me get started. Okay, so this is my last lecture, and this is going to explain Grover's quantum algorithm for search problems. So this dates from 1996, which is only 2 years after Shor's algorithm. And at that time, in the mid-90s, people kind of expected a large wave of interesting quantum algorithms to come. And that hasn't really happened so far. So I think Shor's algorithm and Grover's algorithm are still, 30 years later, the most interesting quantum algorithms that have been found. Of course, there are other things that have been found. For instance, there's the HHL algorithm. There's all sorts of things about quantum walk algorithms, Hamiltonian simulation, etc. You can find all of this stuff in my lecture notes. I don't really have time here to explain these things. But in general, sort of a high-level message that I want to give you is we don't really have that many applications of quantum computers. There's not that many quantum algorithms that we know. And I think this is something that should be a priority of the research community, right? I think for this field, there are two really big questions. One is, can you build a quantum computer? That is certainly not something that I can help with. The other is, what kind of applications could such a computer have? Like, and that's almost synonymous with asking, like, what good quantum algorithms are there? And we need better answers for the latter question. We need more applications. Okay, so I'll just restrict attention now to explaining Grover's algorithm. The good thing about Grover's algorithm is that it solves a very general problem, namely a search problem. You have like a large unstructured search space and you want to find sort of a needle in the haystack in that search space. And Grover's algorithm solves this problem quadratically faster than any classical algorithm could. And you can use this as a subroutine in many other computational tasks. That's the advantage compared to Shor. It's very widely applicable. The disadvantage is that the speedup is only quadratic. So Shor's algorithm gives you an exponential speedup compared to the best classical factoring algorithm that we know. Grover's algorithm really only gives you a quadratic speedup. And that is something that probably will only be relevant for very large instance sizes. Maybe I'll come back to that later, depending on time. So let me first sketch the search problem in some slightly abstract form. So the input is a string of capital N bits. This is very similar to what happened in the Deutsch-Jozef problem. So each xi is a bit. And let's assume that capital N, which is going to be the size of our search space, is 2 to the power little n. This has the advantage that I can address any one of the bits using an I, which you can think of either as an integer between 0 and capital N minus 1, or you can think of it as a string of little n bits. This is the same thing that I said before. I'm always going to sort of go back and forth between integers and binary representations of those integers. So whenever I talk about an I, think of it as a pointer that points to one of the bits here. For computer scientists, this stuff should be kind of bread and butter, but for the others, it might be a little bit confusing. And I'm going to assume so-called query access to X. And what this means is we have a unitary, which I'll call O sub X. O stands for Oracle, which maps I comma B to I comma B plus xi. This is little n bits, and the last item is only 1 bit. Right, so this is a unitary on little n plus 1 many qubits. And let me say a little bit more about where this comes from, because I got a lot of questions after the Deutsch-Jozef lecture about what on earth does this mean. So let me give you a little bit of sort of extra, let me do it here, otherwise the board has to be moved. So what is the motivation for this query access? It's classical random access memory. So what is classical random access memory? It's some sort of box that contains n, capital N input bits. You stick in an index I, and out comes the bit xi. This is classical random access memory. It's not controversial. It happens all the time in your computer, in your phone, etc. This is just what a memory bank is. You have some sort of chip, you stick in an index, and out comes the ith bit of the stored information that's stored in this memory chip. And I sort of want to massage this to become more quantum. And at the very least, I should make this box reversible, because every quantum operation is supposed to be unitary and therefore reversible. And one way to do that is to, this is obviously not reversible, right? Because what goes in is an index of little n bits, and what comes out is only one bit. So I really need to tweak this box to make it reversible. One way to do that is to just let the index I come out again, unchanged, and throw in an additional bit, which is initially 0. And this is like a reversible version of classical RAM memory. Again, this should still not be controversial. And this is almost a unitary now, because it's a map from basis states to basis states. I can put cats around this if I like. And it's not a full description of a unitary yet, because I'm not telling you what happens if I put cat 1 in this qubit. And that's the function of this b here. So I'm going to embellish this a little bit more. I'm going to allow an arbitrary bit b here. And what will come out is not the bit xi, but the bit xi plus b modulo 2. Right, so if I put a 0 here, what comes out is xi. If I put a 1 here, what comes out is like the negation of the bit xi. And this should still not be controversial. This is just a reversible version of classical RAM. And now what I'm going to do is I'm going to say, let me just interpret this as a unitary transformation, namely this unitary transformation. And this is called quantum RAM or quantum classical RAM. Call it QC RAM. And I think conceptually this should be not very problematic, because it combines the sort of the non-controversial notion of classical RAM with the notion of superposition. I will be able to run this unitary on a superposition over many different I's, right? And neither classical RAM nor superposition should be controversial. If you drop the word QC RAM in certain experimental physics circles, people get really upset, because this is going to be very hard to implement in a coherent way on a quantum computer. So let me put that as a caveat here. Hard to implement. There was a question over there. You could leave it at 0, but if you want to specify a unitary, you have to specify what happens to every possible computational basis state that you start with, including when this last bit is not 0 but 1. That's why I stick in the B. So if you think about this as sort of accessing a memory of capital N bits, it's very problematic. In some cases, which I hopefully have time to say something about at the end, it is actually not so problematic. If there is a short circuit, that computes xi from I. And an important case where this actually happens is where you're trying to solve the satisfiability problem. So who here knows what is the satisfiability problem in complexity theory? Okay, hardly anybody. Okay, satisfiability problem is sort of the following very central problem in complexity theory. I'm giving a logical formula which has like little n Boolean variables in it. And my question is there a way to sort of assign truth values to those little n Boolean formulas so that the whole formula becomes true? This is the canonical NP complete problem. If you could solve it efficiently in time polynomial in little n, that would be great. One way to look at this problem is as a search problem where the search space is over all possible truth assignments, of which there are 2 to the little n, right? And if you think about it that way, what is this bit xi? It would just be the truth value of the formula evaluated on the assignment corresponding to I. And in that case, trying to find a location of a 1 here, which is what the search problem is about, would solve the satisfiability problem. So one example where this whole QRAM story is kind of irrelevant is the satisfiability problem. And I actually haven't told you what the search problem is about. So the goal is to find the location of a 1 bit in this sequence. So find an I such that xi is 1, which in the case of satisfiability just means find a satisfying assignment for my Boolean formula, for my logical formula, if there is one. If you could solve this in time polynomial in little n, that would be great. It would show that NP is in BQP, which just seems unlikely. But at the very least, Grover's algorithm is going to solve this problem quadratically faster than is possible classically. Okay, I guess I sort of like maybe put a little bit too much detail here. The main thing I want to say is you can solve this problem here in a time that's square root of capital N. This is not possible classically. If you have like an unsorted search space with like, you know, 1 needle in a haystack and the haystack is size capital N, you're going to have to look at a big chunk of this haystack to find your needle. So the classical complexity of solving this goal is linear in N. And the quantum complexity is going to be square root of N, capital N. Right, so the goal of this hour is just to explain how this algorithm works. How you can sort of search through this large search space in a time that's proportional not to the search space itself, but to the square root of the size of the search space. Okay, so let me give you sort of the high-level view of Grover's algorithm, and then next sort of zoom in on the details and explain those. So as a circuit, it's going to look like this. So we'll start with little n qubits, which are all initially 0. That's not very surprising. Most of our algorithms have started like this. And then we're going to put all these things into a uniform superposition. So the state that we have at this point is going to be a uniform superposition over all basis states I, where I ranges over the strings of little n bits. So at this point, we're going to have 1 over square root of capital N, sum over I, ranging over all possible addresses, ket I. And I'm going to call this state ket U for uniform. Right, so this is sort of the starting point of the algorithm. You make a uniform superposition over all the possible addresses. And this is not unreasonable because what else can you do? Just like this long sequence of bits, you know, in the worst case, only one of the locations is 1. We start from total ignorance, so let's start from a uniform superposition over all the addresses. And then try to concentrate more and more amplitude on the basis states I that are actually solutions to our search problem. And ideally, what we would like to produce, and this is also what Grover's algorithm is going to produce, is something called the good state. And the good state is just a uniform superposition over all the solutions. So this is going to be 1 over some number t, sum over all the i's, where xi is 1, ket I. So t is going to be the number of i's such that xi is 1. Number of solutions, and for concreteness, you can think of t as 1. Right? The hardest search problem you have is if somewhere in this long sequence of bits, there's only one position where there's a 1. The more solutions there are, the easier the search problem becomes. So the hardest search problem is when there's exactly one solution. But in general, I'm going to define the good state as a superposition over all the i's which are solutions. And there's also a bad state, which is the superposition over all the things that are non-solutions, of which there are capital N minus t. So there's a good state and there's a bad state. And of course, they're orthogonal, right? They have disjoint support. The i's that are solutions are in the support here. The i's that are not solutions are in the support here. So these two states are orthogonal. And that means I can plot them in a two-dimensional picture where the good state and the bad state are the two axes of the picture. Sorry, the horizontal axis is going to be the bad state. The vertical axis is going to be the good state. What we like our algorithm to end up with is some state that's very close to the good state. Because such a state, if you were to measure it, you could probably see an I which is a solution as outcome of the measurement. Now, we're not starting close to the good state. How could we? We don't know anything at the start about where the solutions sit. We're starting in this uniform state. And this uniform state here, this has a lot of overlap with the bad state and tiny overlap with the good state. I'm assuming t to be very small, let's say 1 for concreteness. That means that the uniform state that we're starting with is sitting somewhere here. But everything here, by the way, is unit vectors. So this is the uniform state. And you may sort of notice that I have drawn the uniform state in this picture here, suggesting that it is a linear combination of the good state and the bad state, and it really is. So you can write the uniform state as sine of some angle theta times the good state plus cosine of that same angle theta times the bad state. And what is theta? Theta is this angle here. So this is our starting point. So we have an initial state that's very close to the bad state, and we would somehow like to move it towards the good state. And this is what Grover's algorithm does in roughly square root of capital N many steps. So it's going to move this state here slowly, 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 slowly towards the good state by increasing the angle theta step by step. Let's just see what we can say about this theta here. You can just calculate what it is by solving the equations. So theta is going to be the inverse sine of square root of t over capital N. This is just what you get if you sort of calculate what is the amplitudes on the good i's and the bad i's. And both sine and arcsine are essentially linear functions when you put in small inputs. So you can think of this as roughly square root of t over capital N. And in the special case where t is 1, this is like 1 over square root of capital N. So it's a very small angle that we start with. Right, and the goal of Grover's algorithm is to shift this initial state slowly towards the good space. And the way it does that is through so-called Grover iterations, which I'll detail in a second. And it just repeats a number of Grover iterations. And then some state comes out. And hopefully this state should be roughly the good state. And the idea of one Grover iteration is that it will slightly increase this angle theta. Right? And then you do another Grover iteration, slightly increasing the angle more and more and more and more, until the angle at some point is kind of close to 90 degrees, pi over 2, and then you're in good shape. It means you've produced some state that's close to the good state. And how does this magical Grover iteration work? Let me try to explain that. So one Grover iteration G is the product of two reflections. And when I say reflection, it's going to be reflection in this simple two-dimensional picture spent by the good state and the bad state. Product of two reflections. So the first reflection is a reflection of the state through the horizontal axis, so through the bad state. And I'm going to detail in a second how to do that. And the second reflection is a reflection of whatever state we have at that point through the uniform state. So I need to tell you how to algorithmically implement these two reflections. But let's assume for now that we know how to do it. Let's see what effect this has in this picture. Right, so let's look at the first Grover iteration. It starts out with a state that is the uniform state. And then it does this reflection through the bad state. So if you reflect this state through the bad state, where do you end up? You end up an angle theta below the bad axis. Right, so this is what reflection A does. So we are now here. So this is the effect of reflection A. Sort of push the same thing below the horizontal axis. And then you do a reflection through the uniform state. What does that mean? It means that this state here goes like this. So this is the effect of reflection B. And now let's ask ourselves, what is the new angle that we have created with the horizontal axis? Question to you to see if you're following. Right, initially this angle was theta. Now we sort of messed around with our state. We did two reflections. What is the new angle going to be? Right, my picture suggests that it's bigger than the original theta, but how much bigger is it? Like this whole angle here. So, okay, so the thing is that this angle here between cat u and the state of our algorithm, this angle is 2 theta. And then that angle is sort of flipped around. So the total angle that we have now is the original theta plus the new 2 theta. So the angle goes from theta to 3 theta. So what this does is this adds 2 theta to the angle between the current state and the horizontal axis, which is the bad state. Right, so this angle starts at theta. You do one Grover iteration, and it becomes 3 theta. If you do another Grover iteration, another 2 theta is being added to this angle. You can just see that if you do the reflections again, starting from the new state that we have after the first Grover iteration. The second Grover iteration is again going to add 2 theta to this angle. So now we have 5 theta. We do another Grover iteration, we get 7 theta. Right, so you can sort of see if we can indeed implement these reflections A and B, which I still have to tell you how to do, then doing this again and again and again is going to move our state slowly towards the vertical axis, which is the good state where we would like to end up. So after k iterations, the state of the algorithm has become some angle, the sine of some angle times the good state plus the cosine of that same angle times the bad state. And question to you, what should I put here after k of these Grover iterations? What has the angle become? Right, after 0 iterations, it's theta. After 1 iterations, it's 3 theta. After 2 iterations, it's 5 theta, etc. So what do you have after k iterations? 2k plus 1 times theta. Right, and you can do this for any k of your choice. You, the algorithm designer, can choose how many of these Grover iterations to do. But at some point you want to stop, right? You don't want your algorithm to run forever. So what is a good k to stop at? How many iterations should we do?
Cosine gets very small or sine.
Yeah, so what you want to do is you want the weight, or the amplitude in front of the good state, you want this to become essentially 1. Right? Now, for what angle is the sine of that angle equal to 1? It's when the angle is pi over 2, or 90 degrees. So we want to choose a k such that 2k plus 1 times theta equals pi over 2. Because then we've actually rotated perfectly to the vertical axis, and our state, the state of our algorithm, has become the good state, and that's great. If you measure the good state, you're definitely going to see an I, which is a solution. So let's just solve this, and this will tell us what k we need to choose. Right, so we choose k equal to, let me get this right, pi over 4 theta minus a half. So this is the number of iterations we want to choose. And if we choose this number of iterations, we will perfectly rotate the initial state, which is uniform, to the good state. And this would be a good time to complain. What can we complain about? What? Sorry, say again? I'm sorry, I didn't get that. Are you asking for clarification or are you answering my question?
So there's the sine, it's
Oh, so this is 2k plus 1 times theta? Oh, this is the same angle. Right, it's like the angle is going to be the same, and then the projection on the good state is going to be the sine of that angle, and the projection on the bad state is going to be the cosine of that angle. Back to my question. Do you want to answer my question? It's not an integer. That's the problem. Yeah, exactly. So we need to sort of round this down or up, and that's going to incur a little bit of error. So round it to the nearest integer, because of course k needs to be an integer. You cannot do sort of a third of a Grover iteration. Now, this looks kind of funny, pi over 4 over theta. Let's just plug in this approximation that we have for theta. So this is essentially pi over 4 times square root of capital N over T. Right, and in particular in the special case where T is 1, so the hardest problem of the hardest search problem where there's only one solution in your search space, this is going to be proportional to square root of capital N. And this is the basic Grover's algorithm. And of course, you need to know what T is in order to know what K is. But there's tricks to work around this. So, which I will not explain. So there's tricks to work around the fact that we don't know T. You can just basically try out a few possibilities. So let me not go into details there. Or you can just assume t equals 1 if you want. Okay, so all that's left to do here for a full description of Grover's algorithm is how to implement these two reflections A and B, right? Because they together constitute one Grover iteration, and one Grover iteration moves us to theta in the right direction. Yes?
And that we are performing, so the second reflection is done over U, which is constant.
The same U as before, correct, yes. Yeah, it's sort of a coincidence that the initial state of the algorithm and the thing we reflect about are both the same state U.
You cannot do reflection over the previous state, because in this case it will increase.
You could do that, but it's a lot more expensive. So that it is possible to do that, and it will give you an alternative view on the same Grover algorithm. But I'm just going to present it as the reflections are through these two fixed states for every iteration.
But if we reflect over the previous state, then we will each iteration will triple them.
That's right, yeah. And you can present Grover's algorithm that way, but if you do it that way, every Grover iteration will be 3 times more expensive than the previous one. So the number of steps you need to take in your scheme will be much less, because you get exponential increase of the angle, but also exponential increase of the cost of every iteration step. And this, in fact, if you work it out, it balances out to exactly the same algorithm. But I'm going to present it like this. So indeed, in every reflection, in every Grover iteration, we're going to reflect around the same fixed uniform state. So let me just show you how to implement the reflection through B and the reflection through U, and then we're done with the description of the algorithm. Now, there is something funny here that you may have noticed, which is that I'm only working here on a space of little n qubits. But my access mechanism that allows me to access the individual bits xi, this is actually an operator that acts on n+1 qubits. Right, so I did a little bit of a sleight of hand here, which I'm going to explain now. So let's see what happens if we apply our OX operator. So I'm now detailing A, how to do this reflection. So if I apply the OX operator on something that looks like this, right, so now I am actually acting on little n+1 qubits. Then something interesting happens, namely you get the value of the ith bit as a phase in front of the cat I. So this is a little calculation. You could do it on a piece of paper if you like. Oh, sorry, this is not right. So this is a way to convert a mechanism that accesses these bits in an additional qubit, to convert that into a mechanism that gives you access to these bits as phases, as pluses or minuses. And this is in fact the kind of query access that we assumed in the Deutsch-Jose algorithm yesterday. We were assuming you could just get these bits as phases, pluses and minuses. Why is this good? Because if you now apply OX to the good state tensored with an extra qubit that is in this ket minus state. So this state here, maybe I should abbreviate it, is sometimes called ket minus. So this maps, because so all of the i's that are in the superposition ket G are ones where xi is 1. So all of those will have the property that this sign is -1, not +1. So if you apply your OX to this state here, then ket G gets mapped to minus ket G. The good state gets mapped to minus the good state. And if you apply it to the bad state, where this sign is always +1, you just get mapped to itself. All these are sort of tiny calculations that are easy to do. There's nothing deep here. And now let's just sort of like squint and ignore this last qubit here, which is always in the ket minus state. It doesn't really do very much. Then this map is actually a reflection through the bad state. So ket G gets mapped to itself, and ket G gets mapped to minus ket G, and ket B gets mapped to ket B itself. This is exactly, in this 2D picture, a reflection through ket B, through the bad state. Right, and what is the cost of implementing this reflection? It's just basically applying OX1s. You should think of that as very cheap. So the cost is apply OX1s. Okay, so this is the first part of one Grover iteration. One Grover iteration is the product of two reflections, which together induce a rotation. And I just explained to you how to do the first of these two reflections. Let me detail the second one. So one thing that is relatively easy to do, I won't write out the details of the circuit. Oh yeah, question, please. We're assuming that we can, that's written here. That's my assumption. This is how we sort of access the search space, right? And it could either be because there's some fancy quantum memory chip that contains all the bits of X, but it could also be that we have some mechanism to compute the bit Xi given I, such as, for instance, if you were to apply this to the satisfiability problem. So think of this as sort of like a meta assumption. It could be instantiated in different ways depending on the actual search problem you want to solve. Right, I'm treating a very abstract search problem here where the whole search space is just described by a sequence of capital N bits. And depending on the actual search problem you're trying to solve, this is instantiated in many different ways. But all of them will have the property that there will be some way to determine whether or not I is a solution to your problem or not. Right, the only thing that the bit Xi says is I solves my problem or not. So you need some sort of mechanism to decide whether a given item in your search space is a solution or not. Other questions at this point? Okay, so then let's detail reflection number B. So now we want to reflect through ket U. What does it mean to reflect through ket U? It means that ket U should map to itself, and every state orthogonal to ket U should map to minus itself. And this is kind of easy to do if we were to replace ket U by the all zero state. So it's easy to find a map R which maps the zero state to itself, and that maps any string I which is not the all zero state to minus itself. So you can write down a circuit if you want. It's an exercise in my lecture notes somewhere, chapter 2, I think. You can write down a circuit that does this, which uses something like order little and many gates. And you should think of that as cheap. Okay, so now what we would like to do is we would like to, instead of reflecting through the zero state, we would like to reflect through the uniform state. And there's a nice trick to do that. It's essentially like a change of basis, which maps the zero state to the uniform state. And maybe somebody can tell me like how we should massage this R here to get the reflection that we want in part B. Right, you know how to reflect through the zero state. Now instead you would like to reflect through the uniform state. How do you do this? Yeah, you rotate it. And what is the rotation that maps the all zero state to the uniform state? Hadamard, exactly, right? It's in fact that this is how our algorithm starts. So I can take this simple circuit R, which I tell you exists, and you can kind of figure it out for yourself. And if you now conjugate this circuit with Hadamard gates, little n Hadamard gates before it and little n Hadamard gates after it, you get a reflection that we want for part B. So H tensor little n, R H tensor little n is a reflection through the uniform state. Which is what we wanted for part B. So I've now put in as much detail as I wanted for both of the reflections that make up one Grover iteration, right? Doing part A basically costs you one query to the bits of X. Doing part B costs you a circuit of order little n elementary gates. And this is a complete description of the basic Grover's algorithm. And you can make many, many changes to it, and people have made many, many changes for it. For instance, how to deal with the case where the number of solutions T is not known beforehand, how to apply this in all sorts of situations. And maybe to end this lecture, I guess I have about 5 minutes left. Let me just make a list of the many, many applications of Grover's algorithm, just to impress upon you that this is a very useful thing. And then I'll end with a slightly skeptical note. What can I best erase? I think I'm going to erase these details here, because this picture here is good to keep in mind. So let me just give you a list of sort of applications and generalizations of Grover's algorithm, and there's really dozens of them. Is it in focus again? Because I moved the board a little bit. Okay, thanks. Right, so the basic thing about Grover is you can use it in every situation where you want to solve some unstructured search problem. Right, so if you have some big classical algorithm and somewhere inside of it, there's a search problem that needs to be solved, you can hit this with Grover's algorithm and you can get a speed up to that part of your classical algorithm, and hopefully that will translate to a speed up overall. And this has been done in many, many applications. For instance, speed ups for all sorts of graph problems compared to the best classical algorithm. For instance, finding shortest path in a graph. Right, this is a basic navigation problem that your Google Maps will solve for you. You can get a speed up there from Grover. Finding matchings in graphs. Sparsifying a graph while preserving many properties. And this is a long list. There's dozens of papers out there that give you fast quantum algorithms, or at least faster than classical quantum algorithms for many different graph problems. There's many applications of Grover to optimization problems. I'm not going to detail them here, but things like linear programming solutions can be improved, like linear regression problems can be improved. there's a slew of optimization problems that can be somewhat improved by Grover's algorithm. And sometimes the speedup that you get is quadratic if you're lucky. And sometimes the speedup is somewhat less than quadratic, because typically what happens is that only a part of the classical algorithm is improved by Grover, and you still have to deal with all the other components. And then you sort of try to rebalance these components in order to get some overall speedup. And that speedup in some cases is more like a power 1.5 instead of a power of 2. There's a very general mechanism called amplitude amplification. Which goes much beyond Grover. And the idea there is that you have some sort of quantum algorithm which produces some superposition of a state that you want and a state that you don't want, right? Just like good state and bad state here, but in a much more general context. And then you can use something like Grover's algorithm to amplify the part of the state that you would like to see. Initially, maybe it has a small amplitude. You can boost that amplitude to 1 by a mechanism that's very similar to what's happening here. And last but not least, there's a whole class of so-called quantum walk algorithms, which are generalizations of classical random walk algorithms. And initially those look very different from Grover, but you can actually look at them in a way that they sort of quite naturally generalize Grover to random walk settings. This is also the way it's presented in my lecture notes. I put a lot of effort into sort of massaging these quantum walk algorithms so that you can sort of see how they really arise out of this, this typical 2D Grover picture. So quantum walk algorithms can also be viewed as generalizations of Grover's algorithm. And then let me end with a skeptical caveat here, which is important to keep in mind. Right, it seems that Grover's algorithm gives you a quadratic speedup, and who doesn't want a quadratic speedup? But there is an issue here that you have to be careful if you use big O notation to hide the constants. If you have a classical complexity, or the best classical algorithm, has a complexity that scales, let's say, linearly in n. For instance, in an unstructured search problem, that is the case. And you have a quantum complexity that scales like the square root of n. That sounds good. Right, this looks like something that's worth having. But you have to take into account that quantum operations are very, very expensive, especially if you factor in the work you need to do for like error correction. So really this square root of n quantum complexity, it should be multiplied by some fairly large constant, which I'll call c here. And I don't know what it is, but think of it as 10 to the power 5 or 10 to the power 10, some pretty large number. Right, and of course this function here, corresponding to the quantum complexity, for some instance size n, this is going to be less than the classical complexity. And at that point you start getting speed up. But you can calculate when this is going to happen. So from what problem size n do we start getting quantum speed up? Well, it's simple high school math, like for what n does this function become less than this function? Question to you, for what n does this start happening? This is not hard, people. This starts happening. It starts happening when n is bigger than c squared.
Yes.
Yeah, right. And if c is kind of big, as it will be, because one quantum operation is much more expensive and much slower than a classical operation, Then C squared is even much bigger. So really, Grover speedups only start to become effective for very large instance sizes. So let me write that down here as sort of a final thought about Grover. Grover becomes relevant or gives speedup only for very large n. So this is something to keep in mind. Like if there's a startup company, you know, and they say, well, we're going to use Grover's algorithm on near-term noisy hardware, etc., and we're going to make a lot of money with this in 2 years' time, don't believe them. Grover is kind of useless unless you have a quantum computer that's big enough to handle very large problem sizes. Okay, so this is it from my side. Timing is decent, I think. Good. So thanks for your attention. Are there any last questions, either from here or from online? Yes, please. It depends on what C is. So people have made estimates like how much more expensive is one quantum operation compared to a classical operation. And these estimates, you know, they're like powers of 10, maybe 10 to the power 10 or something like that. It depends on a lot of assumptions, like how efficiently can you do the quantum error correction? How much slower is your quantum gate compared to one classical gate? Of course, classical hardware has been super optimized over many decades. Like one logical operation on a classical computer is extremely fast. A quantum operation is much, much slower. It also depends on how much hardware, let's say what hardware you do. I think on superconducting qubits, a gate is relatively slow. On ion trap qubits, maybe it's a little bit faster. So you really have to sort of specify what quantum hardware you're using, what assumptions you make about error correction. But a C that is something like 10 to the 8 or 10 to the 10 is not completely unreasonable, right? And then the C squared is truly massive, which means that Grover's algorithms start giving speed up only for very massive instance sizes. And of course, the hope is that quantum hardware is going to get better and better over time. So this number C will come down, and at some point, you know, maybe the quantum computer will be so efficient and so big that Grover starts having an impact. But don't expect this anytime soon. Yeah. Anything online? Oh, there's a question here. Yeah, please.
The case of graph problems.
Yes.
One can be solved in polynomial time.
Yes.
So do I assume the graph has polynomial size here, or do I assume the graph is finite?
The assumption here is that you're just given the adjacency matrix of the graph. So your input would be like, if there's n vertices, your input would be an n by n matrix, maybe with distances between pairs of nodes. So that's how your input is given. And then classically, you can find the shortest path between 2 points in time order n squared. That's a Dijkstra's algorithm. And the best quantum algorithm, provably the best quantum algorithm, runs in time n to the 1.5. So it's a polynomial speedup, but it's less than quadratic even. Also, something I should have mentioned already, by the way, Grover's algorithm is exactly optimal. There's no better quantum search algorithm than Grover. So you cannot sort of beat the square root speedup, do something better without further assumptions.
Do we know it's optimized for graph problems?
Yes, well, I mean, we don't know it in this case. Like n to the 1.5 is necessary and sufficient for quantum algorithms to find shortest paths in graphs. If the input is given in the form of an adjacency matrix or a matrix of distances.
And here is the number of
vertices. Yeah, so I'm using n for many different things here. Let's say that you have an n vertex graph. That means that the input is an n by n matrix. And the classical complexity of finding the shortest path would be order n squared. And the quantum complexity would be order n to the 1.5 gates. You should think of a gate as sort of one unit of time.
So it has like consumes less time than the input size.
That's right. But the same is true for Grover's algorithm.
Like we represent the matrix as a state, like a.
No, so the idea is that your input is being given as n squared numbers, and the way you can access them is very similar to what you have here. You would just have a sequence of little n squared numbers, and you have query access to those numbers. So in superposition, you could look at many different pairs of vertices, many different edges of the graph. And it has the same advantages and disadvantages as the access mechanism that I assumed for Grover.
So is there a reason why it's or a new algorithm or it's just unlucky?
Yeah, I think there's there's a sort of an answer from incompetence, and there's a very pessimistic answer. The answer from incompetence is that despite decades of effort, we're just too stupid to think in the right way about quantum algorithms. The more negative answer is this is just, it is what it is. Like, we picked the low-hanging fruit. There's probably not much else out there. I'm working on this field, so I'm more of the incompetence attitude. Like if I believed there were no other quantum algorithms out there, I would not even spend time trying to find them. It is just very different to think about quantum algorithms than it is about classical algorithms, right? All of our intuitions that come from classical physics or classical algorithmics, many of them are insufficient for finding quantum algorithms. Okay, thank you.